Okay. Thank you very much for the introduction, and I'd like to thank the organizers, Professor Young-Hoon Kiem, for this opportunity to speak in this conference, welcoming the executive committee members of IMU. I hope you enjoy your stay here and have a nice meeting. Okay, so I'm going to speak about moduli spaces of points on a line, simplest kind of moduli spaces one can think about. And then still there are some open problems, conjectures not solved yet. And I'd like to report some recent progresses. And I try to talk about influences of fields medalist during my talk. Okay, so in math, classification is always a fundamental issue, and we all love to classify. When the classification is attained by a geometric space, we call the geometric space a moduli space. So here's an example. Suppose you want to classify n ordered points in the complex line, C. So I call the set of complex numbers complex line because I like complex numbers. Not, if you prefer real numbers, you would call it complex plane, right? But I always call it complex line. And what is the moduli space? In this case, it's just by definition. The moduli space is Cn. Cn is the set of n tuples of points in C. Okay, second example. Suppose you want to classify n unordered points in the complex line. What is the moduli space? So you would want to think about, okay, the pointer is not working. so you would want to think about the action of the symmetric group Sn on Cn, and this symmetric group acts on Cn by permuting the coordinates. Right? So we want to think about orbit space, the set of orbits, the space of orbits in Cn by the action of Sn. That's going to be the moduli space. But in this case, the orbit space is exactly isomorphic to Cn. So this is the content of the fundamental theorem of algebra. So how do we get the isomorphism? So the isomorphism is given by the elementary symmetric functions, S1 to Sn. And the elementary symmetric functions are defined as the coefficients of the polynomial, which is defined as the product of t minus xi as I runs from 1 to n. So if you expand it as a polynomial in t, the coefficients are elementary symmetric functions in xi's. So that's the map, and then it's obvious that an orbit is mapped to a point. And then the fundamental theorem of algebra tells us that this is surjective. And then it's from this equation, it's easy to say that this map is injective. So this gives us an isomorphism of the Sn orbit space with the Cn. So in this case, moduli space is again Cn. Right, so now we think about your high school days, or some of you elementary school days. You must have tried to solve some polynomial equations. So if solving degree n polynomial equation is now equivalent to an attempt to find local inverse of the map from Cn to Cn, and this map is given by elementary symmetric functions, right? So this is from old memories, I guess, for all of you. Right, so that's good. Those are the first examples of moduli spaces of points in the line. But now, let's make the problem more interesting. I mean, the problems in the previous slide was so easy. Let's make the problem slightly more interesting. If you remember from your high school days or elementary school days, you would remember that the first step in solving a polynomial equation is to apply a change of coordinates. Like x goes to ax plus b with a non-zero, right? So that's the coordinate change you usually apply as the first step. But the goal is to kill some of the coefficients of the polynomial to make the polynomial easier. So we can do that because if you know the root of a new polynomial obtained by replacing x by ax plus b, then you can get a root of the previous polynomial, obviously, and vice versa. So it's okay to apply this change of coordinates when you are interested in solving polynomial equations. So, we think it's natural to think about the change of coordinates as a group. So the group of affine transformations in C is the set of maps from 2C to itself, defined by this equation, x goes to ax plus b. A is non-zero. So that's the semi-direct product of C star with C. C star is scaling, and C is translation. Okay, so now let's modify the problem, moduli problem. The moduli problem now is to classify n-ordered points in the complex line up to change of coordinates. Okay, so what's the moduli space in this case? The obvious thing that we want to attain is that to find a geometric space, which is the orbit space of the affine group action in Cn. And if you want to think about unordered points, then you also have to think about the co-action by Sn. So left quotient by the Sn action, right quotient by the affine group transformation, affine transformation group. But if you think about this for a few seconds, then you realize that these are not very good spaces. You can really easily show that these orbit spaces cannot be Hausdorff because affine transformation group is non-compact and two different orbits can get arbitrarily close, and we cannot separate them by open sets. And a lot of troubles arise if your space is not Hausdorff. Nothing serious, no serious mathematics can be worked out, at least in my opinion, at least in my expertise. So this is a very difficult point. This is a troublesome point, and we have to think about this. We have to address this issue, and I'll deal with this issue later. But one important observation is that on the open subset of distinct points, if you do not allow your endpoints to collide, then all the problems disappear. So everything becomes, if you delete the big diagonal where two coordinates are allowed to coincide, then the quotients are the affine quotient or affine quotient and Sn quotient. They're all nice complex manifolds, and that's very good. So here the observation is that difficulties arise when the coordinates are allowed to coincide. Okay, so let's think about another moduli problem. So what's not satisfactory in the previous problem was that this space Cn is not compact, and also the quotient of Cn by affine group is not compact. And for instance, if you are interested in enumerative geometry, and also if you for other things, non-compact spaces are usually not very useful, because I mean, if in geometry you would like to intersect nice subsets, and if your space is non-compact, intersection of two subsets may disappear to infinity, and that's not good. So we feel very nervous I feel very nervous when I see a non-compact space. My first instinct is always to try to compactify the space. So to compactify the moduli space of points in the complex line, we first compactify the complex line itself. So how do we compactify the complex line? There is a canonical way. There is a one-point compactification of the complex line C. So by definition, the projective line is a set of one-dimensional subspaces in two-dimensional vector space C2. So we all know that one-dimensional vector space is spanned by one non-zero vector. So the P1 can be thought of as the quotient of C2 minus the origin by the action of C star, which is just scalar multiplication. So a point in C2 is represented by two complex numbers, right? Z and W. So this bracket ZW it means the equivalence class or the orbit represented by ZW with respect to the C-star action, which is scaling, this scalar multiplication. So this P1 can be divided into two subsets, two disjoint subsets. The first set is open set when W is non-zero. The second set is the closed set where W is equal to 0. In the first set, I can multiply double inverse to both coordinates. So the second coordinate becomes 1, and the first coordinate can be any complex number. So the first set can be identified with the complex line. In the second set, W is equal to 0, so I can multiply Z inverse to the coordinates. So now the point becomes bracket 1, 0. So we call it the infinity, the point at infinity. So I can see that P1 is the one-point compactification of C. Is compact because it's the quotient of three-dimensional real sphere by the action of the group of complex numbers of length 1. Right, so that's the projective line. That's one-point compactification of complex line. So I call it projective line. We call it projective line. And if you have a 2 by 2 invertible matrix A, then it acts on P2, it acts on P1 as an automorphism. So so the action is just complex, it's a matrix multiplication. Z, W is mapped to A11Z plus A12W, A21Z plus A22W. So we have the action of PGL2. PGL2 is the group of 2 by 2 matrices quotient by the diagonal, the subgroup of diagonal matrices. And that's something sometimes in complex analysis course is called fractional linear transformation. And it turns out that the automorphism group P1 is, this PGL2, these are the fractional linear transformations are all the automorphisms of P1. And then it contains the group of affine transformations. This is three-dimensional, and this is two-dimensional. So one benefit of using projective line to complex line is that we have more change of coordinates. This is three-dimensional, two-dimensional. So it's useful to, when you're trying to solve a polynomial equation, to have more freedom to change coordinates. So it's, in terms of solving polynomial equations, it's also better to use P1 than the projective line than the complex line. So like P1, you can also classify the complex n-dimensional complex space Cn by considering the projective space Pn, n-dimensional projective space. Once again, by definition, the set of one-dimensional subspaces in Cn plus 1. So we take the complement of 0 in Cn plus 1, and then quotient by the action of C star, which is just scaling. Right, so now we can modify our problem. So now we want to classify n-ordered points in the projective line, not the complex line. Then it's also obvious that the moduli space is nothing but P1 to the nth power, right? We are choosing n points in P1. What about n unordered points in P1? So once again, we have to think about P1 to the nth power, and then think about Sn orbits, right? Once again, this is isomorphic to n-dimensional projective space. How do we get this isomorphism? Once again, we think about a polynomial in T, defined by this, Zi and Wi, and then we expand it as a polynomial in T. The coefficients are denoted by Si tilde, and these Si tildes give us this map from P1 to the nth power to Pn, and this is an isomorphism. So this is a kind of projective version of a fundamental theorem of algebra. So, so in this case, so far everything's nice. We have thought about moduli spaces of points in P1, ordered and unordered. They're all complex manifolds, and it is or smooth projective varieties, and these are quite familiar objects that we have right now. So any questions so far? Okay, good. So I'm much interested in...
You don't have here the problem of diagonal when you're not
Yeah. At this point, I'm not applying change of coordinates.
Oh,
Yeah. Without change, with, yeah.
But even as the action of Sn, you can stabilize it, right?
So as an orbifold is different from Pn, but Pn is something called as a set of orbits. It's just Pn. Yeah. So there's an orbifold structure behind it, but let's not worry about this at this point. Yeah, that's a good point. Yes. So as an orbifold or stacks, this guy is different from Pn, but as an underlying set, they are the same. That's a fine point. I didn't want to talk about, but okay, it's actually important. So when I have a moduli space, the first thing I usually ask is the dimension, smoothness, and so on. After that, I ask for the cohomology. I ask for the structure of the moduli space. I mean, structure means how many cells does it have. So let's look at the example. So P1, we've seen that P1 is a one-point compactification of the complex line C. So P1 is C, disjoint union, point. And nth power, you have to take the nth power. Now, you're just taking the Cartesian product, and what do you get? If you expand it, then there is one big open cell of dimension n, and then there are n copies of n minus one dimensional cells, and so on. And there is finally one point here. Likewise, in Pn, we've seen that there is a big open subset Cn, and then the complement is n minus one dimensional projective space. The last coordinate 0 means that you have n minus one dimensional projective space. And so Pn minus 1 contains Cn minus 1, the complement is Pn minus 2, and so on. So by induction, you see that Pn is decomposed into the disjoint union of Pn minus 1, Pn minus 2, and so on. So these types of decompositions are called cell decomposition, and Cn is called n cell, n minus 1 cell, and point is just zero-dimensional cells. So from this, you can deduce cohomology theory. So this cell decomposition can be codified into a polynomial like this. Sometimes it's called Poincare polynomial. So U denotes the complex line C. And U to the kth power means k dimension complex space. 1 denotes a point. Okay? So in the case of P1 to the nth power, the Poincare polynomial is U plus 1 to the nth power. And that if you expand it, then you have a sigma n choose k, U to the kth power. That represents this cell decomposition. Likewise, the P to the nth power, the n-dimensional projective space has this cell decomposition, and the Poincare polynomial is sum of U to the kth power, k from 0 to n. So Poincare polynomial codifies the cell decomposition, and you get this polynomial for the projective space. Yeah. On the other hand, you can also think about graded vector space generated by these cells. So you think about these a graded vector space generated by all these cells here. So in the case of P1 to the nth power, in dimension k, you have n choose k, take k-dimensional cells. So you have this vector space of dimension n choose k at degree k part. So, so this is a cohomology. And then in the case of projective n-dimensional projective space, the cohomology is the direct sum of q, k from 1 to 0 to n. Okay, so I didn't want to go into the definition of cohomology theory and so on. So in this case, this is enough. And on the other hand, and also you can take the closures of these cells and then think about the intersections of these cells. And then these intersections give us intersection pairings on this cohomology. And this intersection pairing makes this cohomology not just a graded vector space, but also a graded ring. gives us a ring structure on the cohomology. So these vector spaces, the cohomology is something that people usually want to understand, and because this cohomology contains a lot of information about moduli space itself. Okay, now we modify our problem again. So we want to classify n ordered points, P1 to Pn, in projective line P1, up to change of coordinates. Now change of coordinate means PGL2, fractional linear transformations. So the moduli space we want is the orbit space of in orbit space for P1 to the nth power acted on by G. And in the unordered cases, we also have to think about the quotient by Sn, and it's the same thing as the space of G orbits in Pn. Once again, because this group G is non-compact, the moduli space, the orbit spaces are not Hausdorff, yes, and bad things can happen along the diagonal. Okay, but on the other hand, on the good part, where all these endpoints are distinct, nothing bad happens, and we give a name for this space. M0n denotes the quotient of P1 to the nth power minus the big diagonal, quotient by the action of G. Here, nothing bad happens. This is complex manifold, although non-compact. The same with this unordered case. So moduli space of ordered points, unordered points, as long as they are disjoint, we have this nice moduli space. So this is one of the main object of interest in mathematics in many different areas. Okay, so in the rest of my talk, I'll be interested in the compactified moduli space of M0n. I want to compactify this way. Okay, so before that, let's talk about some examples. So M03 is the set of 3 points on P1 up to change of coordinates, fractional linear transformations. So we all know from complex analysis that if you have 3 distinct points in P1, you can send them to the standard position 0, 1, infinity by applying fractional linear transformation. So moduli space is just point, because I can send any 3 point to 0, 1, infinity. And M04, what is M04? I have to pick 4 points on P1, but my 3 points can be mapped to 0, 1, infinity. And my 4th point should be distinct from these 3 points. So this is the moduli space. In general, M0n plus 1 is mapped to M0n just by forgetting the last point. Okay? If this moduli space of n plus 1 points, this moduli space of n points, I just forget the last point. We have a forgettable map. And the fiber of this map is going to be just P1 minus n points. You have previously chosen n points, and the last n plus first point should be away from these n points. So this is the fiber diagram. So heuristically, you can think of M0n plus 1 as the product of M0n and P1 minus n points, because the fibers are all the same. So this gives us the Poincare polynomial, more precisely, virtual Poincare polynomial. Poincare polynomial you can assign to M0n is the product of these guys. This guy times this guy, right? Poincare polynomial of this guy is P1 minus n points. And the Poincare polynomial of this guy. By induction, we find that the Poincare polynomial of M0n is the product of u minus k. K runs from 2 to n minus 2. Okay, so that's good. And there are many ways to justify this equation. You can use mixed Hodge structure, or you can use motivic cohomology, and so on. I mean, there are many ways to justify this equation. Yeah, so M0n is not bad. M0n is actually a very nice space. But once again, as I said, I feel very nervous when I meet a non-compact space. I will always try to compactify this. Okay, so we ask for compactifications of M0n. What are the compactifications? And in fact, there are many, many different ways of compactifying M0n. So I'm going to talk about only 2 of the many known constructions in this hour. The first one is historically important, is geometric invariance theory compactification. The second one is the Lim-Mumford compactification. So Deligne is a Fields Medal winner. Mumford is also a Fields Medal winner, 78 and 74. So let me first talk about the first compactification by geometric invariance theory. It comes from invariance theory of the 19th century. In the 19th century, invariance theory was a huge industry, and a lot of important mathematicians have worked on invariance theory. And one motivation of the invariance theory was to construct the orbit space for with respect to the PGL traction on P1 to the nth power. So we start with this thing. So we think about the ring of polynomial functions on P1. So P1 has two coordinates, Z and W, two homogeneous coordinates. And the ring of polynomial functions on P1 is the polynomial ring in two variables. So it's slightly not precise, but you can say it's a section ring or, okay, just let's just say it's a polynomial in two variables, ring in two variables, because we have two homogeneous coordinates. And if you think about P1 to the nth power, then the ring of polynomial functions is a tensor product of these ring of polynomial functions, rings of polynomial functions. And obviously, this is isomorphic to the polynomial ring in 2n variables. Right, if you want to think about the ring of polynomial functions on the quotient of P1 to the nth power by the action of G, it should be the invariant subring of the ring of polynomial functions on P1 to the nth power, right? So it should give us the same number for each of the point in the same orbit. So the famous theorem of Gordon and Hilbert says that this invariant subring is finitely generated. So it means that you can find the finite number of generators and the finite number of relations, and this ring invariant subring can be presented in this manner. So if you know a finite set of generators and finite set of relations, what you can do is you can define a projective variety using those the generators and relations. So these n plus 1 generators define the n-dimensional projective space. They're homogeneous coordinates of Pn. And then the relations f1 to fk give us homogeneous polynomials, and then we can think about the common zero locus of these polynomials. And they define a projective variety. Projective variety means the common zero locus of finitely many polynomial equations inside the projective space. Right. Then you have to ask, so we have a projective variety, which can be a candidate of a compactified moduli space of n points on P1 up to change of coordinates. So the natural question we have now is this projective variety, the orbit space? Mumford says the answer is no, but the answer is yes over an open subset consisting of what he calls stable points. And many important spaces in geometry are constructed by using GIT, including Nakajima-Kuiva varieties and so on. So in this case, this is the stability condition. So let's say Pn is the product of n copies of P1. And the set of semi-stable points is the locus of n tuples of points in P1, where at most half n points are allowed to coincide. Okay, so you have to exclude the points where all the points P1 to Pn are the same, for instance. And the set of stable points is the locus of n tuples of points in P1 where less than half points are allowed to coincide. Okay, then Mumford GIT says that we have a surjective map from the set of semi-stable points, this open set in Pn, to the projective variety we have constructed using classical invariance theory. And inside PNSS, we have PNS, the stable part. If you think about image of the stable part, this image inside the Pn mod mod G, the GIT quotient, turns out to be an orbit space, the set of all the orbits in the stable part. And this is the maximal open subset you can find inside Pn, where this is embedded into the natural projective variety coming from classical invariant theory. And the semi-stable part is the maximal open G-variant subset where the map extends to the projective variety we have constructed. So yeah, that's the best we can do from classical point of view. So this is the best moduli space from 19th century mathematics. So we cannot classify all the orbits in P1 to the nth power. We can classify only the orbits in the stable part. And also, if you allow semi-stable points, then you get a compact moduli space. So obviously, we want to understand this projective variety, the GIT quotient of P1 to the nth power by the action of G. What do we know about this? We know that it's n-3 dimensional, it's irreducible, it's normal. Normal means singularity is not too bad. And when n is odd, the quotient is smooth. But when n is even, there are finitely many singular points, isolated singular points. Some examples, when n is equal to 3, the GIT quotient is a point, m03 was a point. When n is equal to 4, the GIT quotient is just P1. Sorry. And then, and so on. We can work out some examples for low n. And then you want to know, then you would want to understand the cohomology. You would want to understand cell decomposition. How many cells, how many k-dimensional cells does this GIT quotient contain, and so on, right? So that problem was solved in 1980s by work of Frances Cohen, and she could determine the dimension of the cohomology groups, the Betti numbers of the cohomology for n odd, when the GIT quotient is smooth. When GIT quotient singular is more useful to think about intersection cohomology, and she told us a way to compute those intersection numbers, the intersection Betti numbers. In 1990s, Cohen and Jeffrey Cohen found a way to compute intersection pairings also, and that was worked out. For n odd, for n even, I made a small contribution, and then I showed how we can compute the intersection cohomology pairings for the even degree case. Because when n is even, the space is singular, and then for singular spaces, intersection theory usually does not work unless you are lucky. And then if you can use intersection cohomology, intersections, you have nice intersection theory, but intersection pairing should be, is not so easy to compute. And then that's what's done. So more or less, so I shouldn't go into further details about the intersection Cohen's work. So in this case, it's very explicitly, one can compute the Betti numbers, all the Hodge numbers, intersection pairings like this. Let me just emphasize this point that in the PP's Hodge number of the GIT quotient is given as the sum of binomial coefficient, and all the other Hodge numbers are 0. Okay. So when n is even, as I said, intersection theory is does not work very nicely. So you have to think about something called generalized intersection pairing. And there are many ways to think about generalized intersection pairings. One way is to use the canonical way of desingularize the singular points invented by Cohen. And then using that, you can compute the intersection pairing in the partial desingularization. And the formula is given in this manner. And then there are other ways to think about generalized intersection pairings, for instance, by non-reductive GIT. And then that can be also computed quite explicitly by using Jeffrey Cohen localization. And last year, I want to say that I proved a small result with Chen-Jing Bu and it's about generalized intersection pairings on moduli spaces of vector bundles over curves. And there are 4 different ways, and then all these intersection numbers can be compared by Dominic Joy's vertex algebra mechanism. Okay, let's just move on. Okay, so that's all I wanted to say about GIT compactification. And the point is that through the work of many great mathematicians in the 80s and 90s, we now have a relatively satisfying understanding of the cohomology of the GIT compactification. On the other hand, there are also other compactifications of M0n, which are often more useful. So I'd like to talk about the Lim-Mumford compactification in the rest of the talk. So as we observed, difficulties arise when points are allowed to coincide. So the Lim and Mumford's idea is that in order to get a good moduli space, in order to get a good compactified moduli space, you shouldn't allow the points to collide. But there's a price to pay. When you do not allow the points to collide, you have to add more components to the curve. So you have to allow, allow your projective line to degenerate to a tree of projective lines. So previously, we had only one projective line, and we had our mark points here. But now, these mark points, our curve may degenerate into a tree of P1s, and mark points can be distributed like this. So this is a price we have to pay. You have to allow my P1 to degenerate into a tree of P1s. And then the Lin and Mumford told us that then you get a nice compactified moduli space. So in fact, in their paper in 1969, they constructed this moduli space as a stack. But in 1983, Knudsen gave a very explicit construction, inductive construction, and using classical algebraic geometry. And it turns out that this M0n bar suits well with string theory and conformal field theory. From physics point of view, this is the right compactification. So, and also this is very important for enumerative geometry and mirror symmetry and so on. Okay, so let's think about the Lim-Mumford compactification from now on. So in the simple case, M0 bar 3 is M03 bar is just a point, as it should be. M04 bar is also just P1, like GIT quotient case. M03, M05 bar is, now we can choose 2 points in P1 because 3 other points are almost fixed by the fractional linear transformations. So, and then you have to blow up 3 points in P1 times P1. Okay, so of course, because it's this very important space, many mathematicians worked on this moduli space, and they may try to compute the cohomology of the space. Especially in 1990s, it was quite popular to study this moduli space. Okay, so in the rest of this talk, I'll be interested in the cohomology of M0n bar, especially the dimension of the cohomologies. The 2-case cohomology of M0n bar is denoted by BKN. So I'm thinking about k-dimensional cells inside M0n bar. So we would want to know these numbers BKN, the Betti numbers of the cohomology of M0n bar. All these numbers BKN can be put into one function, the generating function, phi ZU. So in the innermost sum is the Poincare polynomial of M0n bar. And then you take the exponential sum of the Poincare polynomials with the new variable z. So that's the generating function of all the Betti numbers of M0n bar. And by the work of Manin, Kiel, and Getzler, this function phi is uniquely determined by this strange functional equation. So if you solve this functional equation, you can determine phi, and you can find all the Betti numbers in principle. I don't want to talk about how you prove this theorem, but let me just mention that this is equivalent to an inductive formula for the Betti numbers. Inductive means that induction with respect to n. Okay, so that's the Betti number. This old result. The formula was obtained about in 1990, about 35 years ago. But I should talk about the influence of field medalists now. So last year, we came up with a paper by Alufi, Chen, and Marcoli. And in their paper, they used the formula I just mentioned in the previous slide to prove that the Betti numbers, bkn, so just forget the n, then the Betti numbers bk minus 1, bk plus 1, they proved that the Betti numbers form an asymptotically low concave sequence. Low concave means that bk minus 1 times bk plus 1 is less than or equal to bk squared. If you take the log, it's just concavity, right? Concavity formula. So asymptotic means that for fixed k, this inequality holds for sufficiently large n. Okay, so we came across this paper and we thought about this paper for some time. And then we remembered Junhee Ha's lecture in 2022, ICM. He said the following: low concavity is very important because it indicates a deeper structure. In his case, it was Hodge structure, and he found Hodge structures in many interesting places, like metroids, and that led to him remarkable discoveries. And so I remembered his lecture, and then sometime last year, summer last year, August 18th to be precise, Jinwon, sitting over there, visited KIAS. So we had lunch together, and it was a very hot day. So we went out to a coffee place near the main gate, named behind me. And we started to think about this problem. What is the deeper structure underlying the low concavity? There should be some deeper structure. So we tried to find some Hodge structures. Nothing, not very successful. We tried this and that. And then after a couple of hours, we thought that maybe probability theory can help us. But there was one problem. I had no knowledge about probability theory. I had never studied probability theory before in my life. So I had zero knowledge about probability theory, except on the high school level. So I had to buy a few books, and then I had to read them from page 1 until I could feel too tired. So here's a quick summary of probability theory that I understand. I understand only this much. So probability theory started in 17th century when serious mathematicians took a problem, Gambler's problem, and the Gambler's problem was this: suppose you finish your game was interrupted in the middle, and what's the fair divide of the money? So that was Gambler's game, and then at that time, the smart mathematicians got interested in this problem, and then they started the probability theory. So we all know that repeated fair coin tosses give us the probability distribution, Cnk, that's 2 to the minus n power times n choose k. It's the probability of getting k heads when you toss a fair coin n times. Yeah, of course, we can compute these numbers very explicitly, for instance, by using Pascal's triangle and so on. But on the other hand, if n is large enough, it's very difficult to compute these numbers quite explicitly, even though we know that we can compute it explicitly. So real difference, real surprise, or real progress was made in early 18th century by de Moivre when he discovered that what matters is the limit behavior of this probability distribution. And he proved that this probability distribution converges to the normal distribution as n grows to infinity. And the normal distribution is the distribution given by this density function, 1 over square root of 2 pi sigma exponential minus x minus mu squared over 2 sigma squared. Okay, so one thing you have to notice is that if I take log of this function, it becomes minus x squared, which is concave. So this function is log concave function. Okay, that's a good sign. And also, this theorem gives us a good estimate of the binomial coefficient for n very large. Okay, let's go back to M0 and bar. This is the end of my knowledge about probability theory. So let me refine the question I put in the previous slide. Let's go back to M0 and bar. Let's think about Euler characteristic of M0 and bar, which is the sum of Betti numbers. So we divide the Betti numbers by the Euler characteristic. So obviously, this gives us a probability distribution. And the question in the previous slide can be rephrased into this question. What happens to this probability distribution as n goes to infinity? Yep, so this is a theorem we proved only last month, maybe 2 months ago. So I was very surprised that you get the normal distribution. So if you think about the definition of endpoints on P1, there's no reason to expect normal distribution, at least for me. It was very surprising. So the other reason why it was so surprising is that if you think about the GIT quotient, GIT moduli space of endpoints, then this is not asymptotically normal. It doesn't converge to normal distribution. But quite surprisingly, M0 and bar, the Betti numbers, converge to normal distribution. And what also surprises me is the variance here, sigma n squared. This n times 3 minus c over 6 times e minus 2. That's very surprising. This is a transcendental number that comes from the geometry of M0 and bar. I have no idea about the geometric meaning of this number, but it should represent some combinatorial complexity of M0 and bar. But anyway, that's the theorem we proved here. So probability theory helps us to understand the syntactic behavior of M0 and bar, the Betti numbers of M0 and bar. So as an immediate consequence of this theorem, we obtain that the Betti number distribution is asymptotically low concave. It can prove even stronger result. So it's not just low concave, it's ultra low concave. Not just ultra concave, it's ultra low concave. Ultra means even if you divide your probability distribution by the binomial coefficient, you still get low concavity. So 3 ultra means you can divide it by the binomial coefficients cubed, then you still get the low concavity. And also we can obtain a very effective estimates of the Betti numbers of M0 and bar for a large enough n. Right, so that's the probability result that I'm an algebraic geometer. I've never studied probability theory before. So this is something I'm really proud of at this moment. Okay, so how did he prove this theorem? So here's the main ingredient. A central in probability theory is central limit theorem. So there are many ways to phrase central limit theorem. Here's one way. Suppose you have a polynomial b of u whose coefficients are non-negative real numbers. And suppose b of 1 is equal to 1. It means that the coefficients of this polynomial give us probability distribution. Okay, now what you think about is that you think about nth power of b of u. Then you get a polynomial, you get a new polynomial, and the coefficients give us another probability distribution. And what you ask for the convergence of this, the behavior of this new probability distribution as n goes to infinity. And the central limit theorem tells us that it doesn't matter which b you start with, you always end up with the normal distribution. That's the central limit theorem that I understand. Okay, and then after reading several books, we found this book by Frajolet and Sedgwick, where they prove a generalization of central limit theorem. They prove that central limit theorem holds even if b of u to the nth power is replaced by a of u times e of u to the nth power. It's just, and I have a factor of a, that doesn't matter. And also, a and b can be analytic functions. So this seems like a natural generalization of central limit theorem. So this is what we did. We applied complex analysis, and we used the functional equation for the generating function of the Betti numbers. And then we found a good estimate for the generating function. And we proved that the generating function can be approximated by in the form of a of u times u of u to the nth power, and b of u is this function. It looks very strange, but this is what we get. So that's the proof. So because we got this estimate by complex analysis and applying the Frajolet-Sedgwick theorem, central limit theorem, we have the previous theorem about the distribution of Betti numbers on the M0 n bar. Okay, so so that's all I know about probability theory. And what I want to add is that all these theorems work for the Fulton-McPherson compactifications, a related moduli space, and we have the same theorem for Fulton-McPherson compactifications. Right, so I have only five more minutes remaining. But let me just skip through what other questions that we can solve with respect to the cohomology of M0 n bar. So another fundamental issue about the cohomology of M0 n bar is the SN module structure. SN, the symmetric group, acts on M0 n bar by permuting the n marked points. So the SN acts on the cohomology of M0 n bar, obviously. So we want to compute the cohomology of M0 n bar as a graded SN module. Right, so that's what we want to do. And there are many open questions, many conjectures about the SN module structure of M0 n bar because it's not still well understood. Okay, so the first natural question, first important question is that each cohomology groups, each cohomology group, I mean twice cohomology group, is a permutation representation of Sn. It means that you have a Sn invariant basis. It means that you can find a matrix representation, which are permutation matrices. And the second conjecture is that Betti numbers form a low concave sequence. We know that it's asymptotically normal, but we conjecture that it's always low concave. Sorry. The Betti sequence is asymptotically low concave, but we conjecture that this is always low concave. And then in this low concavity conjecture can be generalized to strengthened in using a representation theory point of view. So during the past 3 or 4 years with Jin-Won Choi and Donggan Lee, we obtained partial results about all these conjectures by finding combinatorial formulas for the cohomology of M0 n bar as graded SN modules. Okay, let me just, for the remaining 3 minutes, let's just skip through the main ideas. So the main idea is to find a new construction of M0 n bar. And the new perspective we provide is that it's very useful to think about the modularized problem in terms of a much bigger category of stacks, and more precisely, moduli stack of maps from a curve to the quotient stack of C by C star in this case. Oh, sorry, for the remaining 3 minutes, let me try to address only two algebraic geometers in the audience. So this perspective, first you think about very big moduli stack, and then you think about many different stability conditions. That gives us many different compactifications. And by thinking about wall crossing, you can find a new construction of M0 and bar. So let me try to go through basic ideas. We start with the Artin stack, like a quotient stack or the stack of perfect complexes. For instance, when the stack A is BG, point mod G is a reductive group, then the map stack, the stack of maps from a curve to A, is the moduli stack of G bundles on C. This stack was much studied by many important mathematicians, including Christoph here. I learned a lot from his papers. And so this kind of map stack, you can do a lot of things, and many interesting things can happen in this map stack. So this map stack from curves to an Artin stack is very useful in terms of not just the moduli of curves and so on. It's also useful for Gromov-Witten theory, mirror symmetry, for a lot of reasons. This moduli stack is worth studying. So in the case of, so for our purpose, we think about only C mod C star, this Artin stack, and then these are the stack of maps from a curve to this Artin stack. And in that big stack, in the map stack, there are many stability conditions. You can think about change of stability conditions, think about wall crossings of the corresponding moduli spaces, and then they give us combinatorial formula for M0, the cohomology M0 and bar. So what are the stability conditions that we considered? These are stability conditions that are quite familiar to many of people here. So if you have a map from a semi-stable curve to C mod C star, you think about a map from C to C mod C star is equivalent to thinking about line bundle L on C together with a section. And then for a semi-stable curve C, you can think about stabilization map to C bar. And then after stabilization, you get an ample line bundle, omega C bar log. And with respect to the ample line bundle, you can think about the stability, delta stability of Bredlow, Lepotier, Holberg-Land, and so on. And then if you choose a delta, you get a moduli space of delta stable maps. And if you move from delta infinity to 0, then you get a sequence of blowups that connects M0 n plus 1 bar with M0 n bar. So that's how we obtain a new construction of M0 n bar. By applying the blow formula, you obtain a combinatorial formula for the graded SN module of the cohomology as a graded SN module. And the formula looks like this. It's sum over weighted rooted trees, and UTs are some fundamental representations. And that's the formula we have. And using this, we could prove some of the conjectures, at least partially. And then we can also find inductive formulas, and then we can think about some various related problems, solve some of the problems here. Thank you very much. I'll stop here.